Okay. So before lunch, we were discussing that we talk about the earthquake resistant design. We are not going for earthquake proof design. The difference between the earthquake resistant design and earthquake proof design is in earthquake proof design, we are not allowing any damage. Your structure will remain within elastic range. And when earthquake completes, your structure will come back to original position without observing any damage. While earthquake resistant design, where you are not actually designing for the full level of the earthquake force, right? So we have seen that that we are designing for 20% or 30% force, right? 20%, 30% force, right? This is the most important part, I tell you. Actual load coming on your column is 100 kilonewton, is a lateral force. You are designing for 20%, 30% force, and still you are saying my structure is safe, right? Safe in a way is not going to collapse. Your structure may observe damage. Your structure may enter inelastic region, but your structure remains safe. It is not going to collapse during the earthquake, right? So this is a real challenge. You see, when we design our structure for dead load and live load, we are using factor of safety 1.5. So for dead load and live load, the actual load coming on the column is 100. We are designing for 150. And on the contrary, when we talk about earthquake, the actual load coming due to earthquake is 100 kilonewton. We design for the 20% or 30% of the force, right? But still, we are saying my structure is safe. What is the reason? The reason is earthquake resistant design is not a strength-based design. We are not designing on the basis of strength. We design on the basis of energy absorption. We are knowing that earthquake supplies the energy. Earthquake shakes the foundation, and when it shakes the foundation, your structure is shaken and some energy is entering into your building, and your structure has to absorb that energy. Now, how will you absorb the energy? There are two types of things: a brittle material and a ductile material. If it is a ductile, it will absorb more energy compared to brittle, and therefore the ductile design and detailing is very important for us. So here we are talking about the inelastic response. The inelastic response means we are talking about the ductility. So you have to make your structure ductile so that it will absorb maximum energy. So earthquake resistant design is basically not a strength based design. It is an energy absorption based design. So here we are making our structure in such a way that it will absorb the energy supplied by the earthquake. All right. Now, if you look at this 4 pictures, then you will find that whether it's America, Japan, or Turkey or India, the collapse had been observed in the past earthquake. Maybe in India, more devastation had been observed as compared to America, but definitely we are observing damages or collapses during the earthquake. This is the reality. You see, when the earthquake strikes a particular region, suppose if you're talking about the India, then we try to come out of. The reason is we don't have faith in our houses. But I want to share the experience of our commissioner, Dr. Rajiv Gupta, who has visited Japan after the Bhuj earthquake. Right. So they were attending conference, and they were on the 9th floor in Tokyo, one of the building in the Tokyo. So suddenly they feel that something is shaking, the building is shaking, and they have a very fresh memory of 2001 earthquake. So both of them were running towards the 2 IS officers who went to Japan from India to attend the conference. Both the IS officers start running towards the staircase, and they find that all the Japanese people, they were standing in their position, and they are balancing themselves, and they are waiting. They were not running actually. And once the earthquake stops, the Japanese people have clapped, and they said that it's over. Right? You see, so these people having the faith in their building, they know that from the 9th floor, they never come to the ground floor during earthquake, because earthquake event is maybe a 1 minute or 2 minute event. And during that 1 minute or 2 minute, you cannot reach to the ground floor from the 9th floor. It means the advanced country like Japan is considered to be the best as far as earthquake preparedness is concerned. They are ready to face any earthquake. But if you look at 2011 earthquake of Japan, right? What happened actually? 2011, Japan has experienced an earthquake of 9 magnitude, right? And basically, the Almighty God has decided that, okay, I am selecting Japan for the earthquake so that it will give good message to the world that you have to prepare yourself for the earthquake. If you don't prepare, then you have to pay the prices. So God has selected Japan, and 9 magnitude earthquake came into Japan. And after earthquake, God has observed that, okay, what happened to Japan? And God realized that almost nothing was happened. Almost Japan was safe after 9 magnitude earthquake. So God was surprised. What is this? So the God came up with the second Brahmastra, that is the tsunami. Right. Now, when the tsunami comes in Japan, then numbers of people died, more than Bhuj earthquake. So people died because of tsunami, not because of earthquake. The reason was, actually, Japanese were knowing that their country is prone to severe earthquakes. So they have constructed a building which will resist earthquakes. So they are making lightweight structures, but these lightweight structures are more vulnerable in tsunami, and a tremendous devastation had been observed because of tsunami. The God was not still satisfied. God has said that, okay, I want to give some more message. And then the third disaster came in picture. It was a nuclear disaster. The Fukushima power plant. The Fukushima power plant observed a damage, and there was a nuclear radiation, right? So nuclear disaster came in picture. So Japan earthquake of 2011 is known for the triple disaster, right? And after the nuclear disaster, the world was shocked. The world was shocked, and world was saying that, okay, this, like, Japan is the country which is ready for the earthquakes. They have a wonderful policy, nuclear policy and everything, and still they have observed tremendous devastation. Then we have to think about the earthquake. So the whole world has stopped the nuclear policy, nuclear programs, and they start thinking of their nuclear policy. And after 6 months or a year, they came up with the new policy, and I think that makes a lot of difference. So Japan earthquake was a great earthquake, and it is known for the triple disaster. So that earthquake, the damages or collapses observed because of not because of earthquake, but it was because of tsunami. Now, if you look at this, we say that the collapse is observed, and what is the reason for the collapse? The reason of the collapse is the deficiency in the building, and this deficiency may be local or global. What we mean global deficiency? The global deficiency means if any damage or the collapse is taken place of an element, then it will lead to the collapse of the whole building. This is the deficiency we are talking about. And local means you have damages at certain locations in the building, which may not lead to the complete collapse of the structure. So we will talk this deficiency one by one. So various irregularities, like stiffness irregularities you have, which is known as a soft story, extreme soft story, mass irregularities, vertical irregularities like setbacks, the in-plane discontinuity of vertical members like floating columns you have, discontinuity in the capacity, the weak story, and open ground story. So if you look at this, you see this is a very poor building, right? Here what is happening? Generally, in Gujarat, a balcony was permitted before 2001. A 4 feet balcony is provided. So what the people were doing? They are covering the balcony, right? They cover the balcony and they enlarge their rooms, and so what they do, actually their wall should come here. Wall or column should come here. Instead of that, what they do, they go for this cantilever and then they are taking column from it, right? Column like this. So what is happening? This column is taking the load for of this floor in this direction, right? It is taking this force in this direction, and at this particular point, now this column don't continue up to the foundation. So now this column is resting on this beam. This column is resting on the beam, right? So here you can see this column is resting on the beam. So this vertical load which is coming of the column, which become a shear force in this particular beam, and this beam carries large shear, and we know the shear failures are the brittle failures, and therefore we have observed the damages of these balconies during the earthquake, right? Now you see, this is a very awkward load path, very awkward load path. Now here the load is coming like this, right? And vertical load, then you are transferring in the horizontal direction, and then you are transferring in this direction. So this is a very awkward load path, and therefore these buildings are not performing good during the earthquake. And in earthquake is having the vertical acceleration, and this vertical acceleration causes a tremendous damage in the beams. This beam is vulnerable to the maximum damage, I tell you. And we have observed the collapse of these balconies during the 2001 Bhuj earthquake. Now here you can see, here basically we need a larger opening here, right? We need an opening. So this column which is here, it is resting on this beam, right? So it is transferring load like this. So this is not a good load path. So load path must be good enough. So I'm always saying that the forces are flowing like water, right? If you design like that, your structure is good, right? Suppose if a column is here, and if the column is here, definitely this will perform much better as compared to the columns are supported on the lateral beams, right? So it is a poor design, I tell you, and it is not going to perform well during the earthquake. Then we move to the the most important aspect is the open ground story. Open ground story. Open ground story means a ground floor which is used for the parking. This is used for the parking, right? When it is used for the parking, you will find only columns here. You find the columns here. But on the first floor, you can see you have a column here as well as the wall. Column plus wall. So the ground floor is flexible. Ground floor is flexible because only columns are there. On the first floor, you have column plus wall. So there is a huge difference in the stiffness. The stiffness of the first story is high as compared to the ground story. So here the stiffness of the ground story is very less as compared to the first floor. And what is going to happen due to this? Now again you can see this is the open ground story. Again this is open ground story. So what is going to happen then? The upper part. This upper part will behave as a rigid body or a single unit, and when the load will come, then the whole building is moving, right? And as this ground story is flexible, so the total deformation is concentrated on the ground story, right? And therefore this ground story observes a larger deformation, and greater damage is observed at the ground story. So we are knowing that this deformation must be distributed along the height of the building. Instead of that, the most of the deformation is concentrated on the ground story. Here you can see this is a regular building, and in the regular building the total deformation is delta. Now this delta is distributed at all the floor level, right? At the floor level. While in case of a soft story, what is happening? the maximum deformation is at the ground story, and almost it will remain same, right? So this is known as a soft story effect. And in 2001 Bhuj earthquake, Ahmedabad, Gandhidham, Bhuj has observed tremendous damage to the soft storage structures. Right. The soft storage, generally we are providing parking at the ground story, and for that we are compromising with the structural systems, and therefore a collapse has been observed. In Ahmedabad, 128 building collapsed. Out of that 128 building, 90 to 95% building collapsed because of the soft story effect. Poor workmanship was there, poor structural design was there, poor quality control was there. It is already there, but the one of the main reason is the soft story effect, right? The soft story effect is the worst effect ever observed in 2001 Bhuj earthquake. If you look at this, this is the soft story, and here you can see this is the columns on which the whole upper stories are supported, and if you look at this, the upper story are working as a unit. Means these are the very steep part, and they are moving as a rigid floors. And here the total deformation is considered the ground story, so it is behaving like an inverted pendulum, right? So what is happening, you can see here, this is the damage you can observe. It is a poor design. Even here the closed stirrups is required, it is not provided. If you look at this, then this upper story, seems okay, but the ground story columns, they were collapsed, right? So this is a soft story effect. Here you can see the upper story is absolutely fine, right? But these ground story columns were collapsed. The many people are saying that our buildings sink by 1 floor because of earthquake. It was not, sinking of the ground floor is not taken place. The columns were collapsed, right? Columns were collapsed. You can see this. This is a observed in 1970 San Fernando earthquake of USA. Now here, if you see, there's a beautiful mountains. So the person who is living here, he said that, okay, I want beautiful views of the mountains. So what he did, the columns are there, but instead of wall, he has placed the glass panels. And when he placed the glass panel, this ground floor converted into a soft story, because the glass panel don't have the enough stiffness, right? And you see, I told you, earthquake will identify deficiency within 2 minutes. Earthquake don't require more time, right? So earthquake is a Maggie force. As far as I'm always saying earthquake force is a Maggie force, right? Because it is checking all the buildings within 2 minutes. You can see this. The ground story columns were collapsed. The upper part is generally almost intact, right? Some damage is because of the collapse of the ground story, right? This is a classical picture. Now this is the picture. You can say it is a soft story failure. At the same time, the structural elements are unsymmetrically placed, so torsion also came in picture. Torsion, right? And therefore you can see the failures like this. So open ground story plus torsion, both are the reasons for failure of this building. This is a very beautiful building in the Switzerland, and it looks very beautiful. But when the assessment has been done, then it was found that this building is vulnerable, and this building may collapse during earthquake. So they have retrofitted this building, and they issued the notice, and then it was retrofitted later on, right? So what are the remedies of soft story effect? We are knowing that on the upper story we have column plus wall, right? Column plus wall to have. So if you provide the walls at the ground story, then problem is solved of the soft story, because the stiffness of each story will become same, right? This problem can be solved. But here, what is the problem? By placing the walls, you are sacrificing parking. So parking you cannot have in this kind of solution. So it is not acceptable. So what can we do? That we are going to place a shear wall. We are going to place a shear wall here, and we are going to place the shear wall such a way that it is symmetrical in nature, and we allow a passage for the car to park, right? So you have to design the shear wall such a way that you have enough opening, and generally a 20%, 30% shear wall will work, and the rest of you have to plan the shear wall such a way that the parking can be possible. So this shear wall, we said that it should be placed symmetrically, right? This is the most important aspect. If you place the shear wall on this side, the shear wall should be placed on the other side also. Shear wall on this side, shear wall on this side. It must be symmetrical in plan. It's required. Otherwise, if you are not placing the shear wall symmetrically, then torsion will come in picture. And we'll see what will happen if it is unsymmetrically placed. So this type of things is not desirable, unsymmetrical location of the shear wall, because it introduces torsion. But you have to place a shear wall like this, which is placed symmetrically, and it performs well. If you look at this, it is placed symmetrically, one on this side, on back side, same way here, on the back side it is provided. So placed very symmetrically, and it continues from top to bottom, which is important. Shear wall should not be curtailed at the first story. Remember, this is very important. And the shear wall construction is also very easy. Nothing is not difficult. So when the lateral load will come, then this side will be under tension, this will be under compression. So this is under extreme compression. And when it reverses, the force reverses, then this side will come under compression and this will come under tension. So both the sides comes under extreme compression because of the lateral force, right? So to resist the compression force, because compression is maximum at the end of a shear wall, and therefore what exactly we need, we have to provide a boundary element here, and this boundary element, or you have to place the shear wall between the columns. Columns is having a larger section, and therefore it will resist the axial force because of the lateral force in a nice manner. So this is the detailing of the shear wall, and this is very easy. You can see here, this is the shear wall. The reinforcement, it depends what is the thickness of the shear wall, 200 mm, 300 mm. So you require a 1 layer of reinforcement or 2 layer of reinforcement. It is decided by the structural engineer, right? But the important thing is your shear wall must be between the columns or the boundary elements, right? Because the maximum axial compression is going to come here. Maximum axial compression is going to come here, right? So this part must be having a larger axial force capacity. You can provide the boundary element like this, of the same size. It depends, right? So this is without increased thickness, and this is with the increased thickness. Or ideally, if you can place the shear wall between the two columns, that is the best thing. So column will work as a boundary element in that case. So here you can see the construction of the shear wall. Already we have pictures. Now you can see this is a this is the two shear wall. It's a coupled shear wall on all the faces, right? So this is the office building in New Zealand, and the coupled beam, the coupled shear wall. So it is like detailing is for tomorrow. The professor will discuss this detailing in detail. So today we are not discussing. So when it is to be required, you see this shear wall is continuous, and then you have some openings here. So you have to detail this part properly too, because when you go for the opening, the stress concentration will be taken place, and when the stress concentration taken place, you have to go for the detailing in such a way that it will take care of that stress concentration. Right. So, very well-known consulting engineer in USA, Mark Fintel, he said that we cannot afford to build concrete buildings mean to resist severe earthquakes without shear wall. The shear wall is the most important element, and you see, as far as Indian condition is considered, if I consider, then the shear wall is the best option available to make your structure earthquake resistant. Shear wall is the best option, right, under Indian condition, right. So this statement of Mark Fintel is most appropriate for the Indian structures. Suppose generally the shear wall we are providing for the RCC structure, but when we are talking about the steel structures, then the another option is also available, and that is the bracing. So generally we are providing the bracing here, and the purpose of the bracing is also to increase the stiffness. Purpose of the diagonal bracing is to increase the stiffness, right? The purpose of shear wall is to increase the stiffness, right? So when you provide a shear wall, the stiffness of the first story and stiffness of the ground story will become almost same. Same way here in the steel structure, we are providing the bracing. It will increase the stiffness so that the difference in the first story and the ground story stiffness will become negligible, right? So you can see here it is placed like this. These are the bracing provided, right? And somebody saying that, okay, I don't want to go for bracing or shear wall, then definitely code is not let them allowed to go. So the code is saying that you have to design the ground story column for 2.5 times earthquake force, right? So when you design for 2.5 times force, then the sizes of the column will become bigger. Size of the column will become bigger, stiffness will increase, and the difference between the stiffness of the first story and ground story will become almost negligible, and soft story effect can be avoided. Sometimes the soft story is observed on the upper story also. If you look at the upper story, here a soft story is created, right? So what is happening that here your floor will become flexible. Upper part is rigid, bottom is rigid. So this is an intermediate soft story. For example, if you look at this, sometimes the people are saying that, okay, I want an auditorium on the second floor or third floor or 10th floor. So when you provide the auditorium, you are curtailing the columns, and by doing that, or you are avoiding the walls. In that case, it will become soft. And I told you again, within 2 minutes, the earthquake is going to identify this deficiency. Earthquake can reach to any floor within 2 minutes, I tell you. And I think this is the intermediate soft story failure had been observed. Here also you can see, here actually it was an open ground story, but what happened? The builder has constructed this shops illegally after the construction of the building. So soft story was avoided on the ground story, but there was a soft story on the upper part, and immediately it was identified and it was checked and met. This is gone, right? Then next part is we talk about the short column, right? We talk about the short column. Short column means suppose if my building is on a slopy ground, right? Then this column is the short as compared to this. So height of the column is different, right? Same way, sometimes height of the ground story column is more. So we generally provide a mezzanine floor. When we provide the mezzanine floor, then the column height become almost half in that case, right? Now this short column is good or bad? Short column is good or bad? Right. Here you can see here again, this is the building in which a partial construction is there, right? Only construction up to this is been done. So what happened now? This column is having the full height, right? Full height. So it can deform by the full height. But here what is happening? Now you have a masonry side, you have a masonry on this side. So this column, only this column can move. So not full column, only the half of the column can move. So this is a short column. Now, can anyone write in the chat box, short column is good or bad? Short column is good or bad? Please write in your chat box. Is bad? Is a good? Bad, bad, bad. It's bad if not designed properly. Bad, bad. Okay. Anyone not good? Not good means bad. Okay, it is bad. Bad, bad. All of you are saying bad. Most. So if it is a democracy, then the bad will win. Depends on stiffness. It is bad. Bad if not considered as action. Bad failure in crushing. Good. You see, the most important part is neither of you are correct. We have to be very specific when we give the answer. So if you look at this, then this is a tall column, this is a long column, and this is the short column. Now, suppose I'm knowing that if this is a column, when the axial load will come on this column, and the another is a short column, and when the axial load will come on the column, then definitely for the axial load the short column is good, because in standard column buckling will take place, right? The short column is good for the gravity loads, for the axial load, right? But in case of earthquake force, when the lateral load is acting, then what is going to happen? Now we are knowing that the earthquake force of earthquake is actually distributed as per the stiffness of the vertical element. It depends on the stiffness, right? Now if you look at this, what is the stiffness? Now suppose if I consider both ends are fixed and the mass is not allowed to rotate, then the stiffness will be 12 EI upon L cube, right? So if the height will become here, suppose the L become L by 2, then what is going to happen here? The stiffness of this column become 12 EI upon L by 2 cube. So it is almost 8 times into 12 EI upon L cube. 12 EI upon L cube, right? So the short column is going to attract 8 times more force. 8 times more force, right? As compared to this. So for the lateral loads, the short column is not good. For the vertical load, short column is good as compared to the slender column. But as in case of earthquake, the short column is going to attract larger earthquake force, because the earthquake load is distributed as per the stiffness of the vertical elements. It is earthquake force, it K into X, right? And therefore you can see here, now this actually the column we are designed for the full height. This is the height is L, and you see this is the ground story column, and when the The residents have find that, okay, we need a security, so they constructed a compound wall. They have done nothing wrong. They have done nothing wrong. Only the concepts are not there. So when they constructed this wall, so what was happened? This column is confined from this part, and only this column is able to move. Now, what is the height of this column? Is L by 3. L by 3. Right? This is total height. So, what is the stiffness of this column? The stiffness of the column is 12EI upon L cube. So now, this column is going to attract 27 times force, 27 times. 3 3s are 9, 3s are 27. 27 times force this column is going to attract. And that is the problem. You see, here our intentions are not bad. We have constructed a wall, which is a compound wall, which is only for the functional purpose, but it interferes with the performance of the column. And therefore, what happens? Actually, we have designed our column to vibrate with the full height. But now it is not vibrating with the full height. Only L by 3 is allowed to vibrate. So it will become stiff. And when it becomes stiff, it tries to attack 27 times force. And I think this is the result. And I'm not saying this is the only reason, but here the poor detailing also. This is very poor detailing. I think the closed stirrups we required at the top and bottom of the column, which is not provided. So this is a very poor detailing, but it is a short column effect. You can see this is a short column effect. Again, the poor detailing is there, but this is a short column. So short column is not good if during earthquake, because it is going to attract higher force. But if you know it is a short column, there is no problem. You have to design the short column, right? You have to design for the maximum force. This is the example of multi-story car parking in California, right? So actually this column is designed for the full height, right? This column is designed for the full height, but when this parapet is provided for the safety of the car, this column becomes short. This column becomes short, and it attracted almost 8 times more force. And then we see the result, right? We see the result that I'm just telling you, within 2 minutes it reached to any floor. It identified the deficiency and punished these elements, right? This is a wrong design. You see here, nothing is again wrong. We have designed column for the full height. Only when we provided the parapet wall, then the parapet has confined the column, and when it confined, it becomes short, and when it becomes short, it attacks higher earthquake force, and damage has been observed, right? Here again you can see this portion. This column is designed for the full height, right? But what happened? The masonry is provided here. So instead of the full height, this column becomes short. And when the column becomes short, it is gone. It attacks higher earthquake force, and you see, nature is also giving the sign. Which sign nature is giving? You can see this sign. Don't do this practice. Don't do this practice. Right? Now, you can see another example of the short column, right? Another example of short column. Now, this is a typical failure. I think you will observe in malls right now. These malls, if you have visited, you have noticed that in the mall the height of the ground floor is maybe 15 feet. So what they do, they provide a column, 15-feet column you have, and in the 15-feet column they have a walls up to 10 or 12 feet, and then upper 3 feet or 5 feet they provide a glasses for the ventilation purpose, right? Now these malls are coming up with the flat slab technology. The flat slab they are using. Now when the flat slab is there, the thickness is very high, so mass is increased. If the mass is increased, then earthquake is the mass into acceleration. So in case of a flat slab, the earthquake force increases as compared to the normal slab, first of all. The second is, they are, instead of providing the full wall, full wall up to 15 feet, they provide 3 feet or 5 feet a glass panel or glasses for the ventilation purpose. Then these all malls will observe short column failures in future, I tell you. And most of the malls came after 2001 earthquake. So remember, when you visit any malls for the entertainment, also look at the structural part also. And in my opinion, in the next earthquake, these malls will be the ideal for the short column failures, right? And you will see lots of short column failures in future when earthquake comes. Here again, you can see this is a short column. It is gone, poorly designed. This is very poorly designed, right? You can see this is very poorly designed. So what is the solution? The solution is the problem arises when we are not allowing this column to move for the full height, right? So solution is you allow this column to move for the full height. It means you have to allow the separation of masonry wall with the columns, and you have to allow this column to move freely. This is a simple solution, right? So separation of infills from the frame, right? And then the gap, it is to be filled with the proper material, right? So close the gap details. And sometimes people are saying that suppose if we are not able to avoid short column, then only answer is you have to design short column. That's all. And the short column means this, suppose this portion is going to attack larger force, then confinement of the reinforcement is the solution, and you have to design this column properly, right? Then we have we talk about the plan irregularities, right? The torsion irregularities, re-entered corner, diaphragm discontinuous, out of plane offsets, non-parallel systems. So numbers of things we have. So generally, what happens when we go for the actual design of the structure, then most of the time architect govern. Architect is always saying that on the front side, don't put the shear walls and all that. It is required for the elevation. So generally, suppose the entry is on this side or is on this side, then the shear walls or the lift well is placed on the rear side, right? So am I audible? Am I audible? Hello? Hello? Am I audible? Okay, fine. So generally, the front side of the building, we are generally not allowing the shear walls. So the lift well, which is placed on the back side, so this part will become stiff, and this part will become flexible. If you look at this, picture, then this part will become stiff, and this part become flexible. So when earthquake comes, then this part will move more, and this part will move less, right? So the different movement is going to take place. And if you look at this building from the plan, then you will find that it undergoes the twisting. Center of mass and center of stiffness both are not matching, and in that case, a torsion is going to introduce in the system. So if you look at this is the L-shaped building, and in case of L-shaped building, the center of mass and center of stiffness never matches, and in that case you have the failures here, right? You can see here the same thing is because of the torsion, the failure is here. You can see the front portion is quite flexible, back you have a walls, so it is failing like this. Here again, this is another example, right? This building is on its knees, right? Now here you can see this is actually seems a good design. Now this is the tubular steel truss columns. These are the right. Generally, these are not taking any load. But when earthquake comes, when the lateral movement starts, then these columns are under tension, right? And it start taking the load, and it will insert it to reduce the torsion as a retrofitting measures, right? So this is introduced to reduce the torsion effect. So the Henry Tegencall, who is a well-known structural engineer, he said that if we have a poor configuration to start with, then a structural expert can do only the band-aid to improve the poor solution as best as he or she can. It means if architect is giving us a very poor configuration, then good structural expert cannot do anything. It just provide a band-aid. But on the contrary, we can say if the architect is giving the good configuration and the framing system, then the poor engineer cannot harm its ultimate performance, right? So if the configuration given is good, then almost half of the battle is won, I tell you, right? So good configuration is the one of the major thing, right? Then we talk about the integral action. In earthquake, the integral action is the most important, right? Now we will see exactly what is happening, right? You see, this is the building. Now this building, you have a shear wall here, right? This is the lift well. Lift well is generally made up of RCC. So when the walls are made of RCC, it behaves like a shear wall. And when it behaves like a shear wall, it is going to take a earthquake force nicely. But here what is happening? This is the main building. Now this main building is not properly connected with this. It is not connected with this, right? It is not properly connected with this. If it is connected properly with the strong elements, then the force of this main structure may be transferred to this, and this shear wall or this lift well may support this building, and it is possible that building might have survived. All right. Then the improper connection of the overhead water tank. Right. Now here what is happening? Generally our concept is we are putting the water tank at the top, and to place the water tank, what we do? We identify 4 columns on the top story. 4 columns we identify, and then we put a bottom slab, and then the side walls, and the top slab, and your water tank is ready. So we identify 4 columns, and we design that column for the load of the water, and we are not designing for any other. Only we design for the gravity loads, right? That is the problem. And what is happening? You see, when we are placing our water tank on 4 columns, so basically this water tank is okay as far as the vertical load is concerned, but when earthquake comes, then it is going to shake in the horizontal direction, so it behaves like a cantilever. So this water tank is actually a cantilever supported on 4 columns, right? And this collapse you can see here, this collapse had been observed. The reason is we have not designed this column to take the lateral force, right? That is the problem. And the IS code is saying, IS 1893 is saying that when any projecting part, see now this water tank is projecting from your building, so it is a projecting part, and when the earthquake force comes in picture, you have to design this water tank for the 5 times earthquake acceleration, right? So any projecting part you have to design for 5 times acceleration. It is not done, it is gone, right? Here again you can see this is also gone, because this water tank are not designed for the lateral force, or the supporting structure of this water tank is not designed to take the lateral load. That is the problem, and we have to consider that, right? When the 2 structures are very close to each other, they will hit each other, right? It is known as a pounding. Now generally we observe in such kind of situation in old cities where the problem of the space is there. So in that case, what is happening, that we have designed this column for the earthquake force. We have designed for the earthquake force. So this both the structures are designed properly for the earthquake. But what is happening due to the lateral movement here? This slab is hitting this column. Right? When this slab is hitting the column, we have not designed this column for the impact, and we know the impact force is having a double effect as compared to the gradual load. And then if your column is not able to take the energy which is given by this impact, then this column may collapse, right? So this is known as a pounding of structures. And you can see here the failure is observed. Here you can see because of the pounding, the weaker structure will collapse, right? Stronger structure will survive. Look at this at the top, the pounding taken place and the weaker structure collapses. It means when two buildings are, what is the solution? Solution is when two buildings are close to each other, your structure must be stronger than the adjacent structure. No, that is not the solution. Solution is basically you have to design the gap. You have to design the gap. Now, what is the gap? Gap means we have to assume that both the buildings are moving in opposite direction, right? Both the buildings are moving towards each other, right? And we calculate the top deformation. Right? And as per the IS code, it is the drift which is allowed, which is 0.004 h, 0.4% of the height of the building. And so what is the maximum expected lateral displacement? It is 0.04 h into response reduction factor. So this is what the deformation allowed, lateral displacement, right? So we have to design this gap on the basis of this, right? We have to design the gap, and we have to design in such a way that they should not collide like this, but the sufficient gap is available, right? This gap we have to design, right? So they should not collide with each other. Building with the setbacks. Now these are the buildings, right? Now if you look at this, these are the buildings where you will found a sudden change in the configuration at certain point. For example, if you look at the bottom part and this part, so there is a huge difference in the stiffness at this level, right? There are numbers of columns on the lower part, then it reduces suddenly. So there is a sudden reduction in the stiffness of the building. Here also, like a lower part is having the higher stiffness, upper part is having flexible, right? So they are not going to perform well. So what is the solution? The solution, Dr. Murthy correctly said that it should be simple and symmetric. Don't make a complicated structures. So if you if it is your vertical setback, separate the portion and then try to make it as simple as possible by providing the separation gap, right? So here you can provide the separation gap like this, right? Now we talk about a local deficiency in the building, the failure of the flexural members, right? Now if you look at this, this is the beam, and this beam is actually failed here, and you can see here confining reinforcement is very less, right? And this is the reason the beam is failed. Now because of the failure of the beam, the whole structure is not going to collapse, but it is a local level failure you have. Here you can see the buckling of the bottom bars. This buckling is taken place, it means there is a large axial force comes in picture, and therefore this has happened. This is a very rare phenomenon, I tell you, buckling of the longitudinal bars of the beam, which is a very rare phenomena, but it is taken place during the 1985 Mexico City earthquake. Now what is happening? When we are talking about the gravity loads, when the load is acting in the vertical direction, then we are knowing where the tension is coming. We are knowing that in the beam, tension is coming coming at the center of the beam, and then at the center you have tension on the upper side, right? And same way you can identify the tension, right? These are the tensions, right? But when the earthquake force is going to act, then you see it is a lateral force, and in case of lateral force, when the earthquake force is acting in this direction, then you see this and these are matching. Okay, fine, no problem. But what about this and this? It is totally changed, right? Same way, suppose this and this is okay, but what about this and this? It is completely changed now. Same way, when the reversal is taken place, because earthquake is taken place in both the means shaking is taken place, so earthquake force will act in both the direction. So its tension and compression numbers is keep on changing. And if you draw this, then you will find that here when the movement is in this direction, then this is what you find, bending moment, and here you have this bending moment, right? So we have to provide, you see, here you can see where the tension is coming, right? That we have to see here. It reverses in the up, it is reverses. So basically you have to provide a reinforcement on both faces of member, right? That is required. It's because of the earthquake shaking reverses the tension and compression in the members, right? Then confinement and the anchorages. Now tomorrow it will be discussed in detail. So today I'm not going to discuss much, but you see the flexural failure will take place where the maximum moment is there. So in case of symmetrical beam, it is at the center, and when it is a simply supported, at the center the maximum moment and the flexural crack starts from this, and at the end you have the maximum reactions, and therefore because of the maximum reaction the shear crack will appear at the support. And therefore we are saying that here you need a closed stirrups, you need a closed stirrups here, and in between you provide a lapping, so you need a closed stirrups in the middle, right? So where the important thing is when you do the lapping, this is the lapping. So during the lapping you have the confinement of the reinforcement, which is very important. So confining steel is provided, right? And tomorrow the Professor B.J. Shah will discuss this part. And the important thing is anchorages. When the shaking starts, your tension and compression is keep on changing, so your bar will try to come out. And if you don't provide the anchorages, then integral action cannot be achieved, and that is the problem with the structure. So enough anchorages to be provided. Tomorrow again I'm saying it will be discussed by Professor B.J. Shah. If you look at this, basically we are providing 135-degree band, which is important. 135-degree band is required so that this stirrups will enter into the concrete core, and during the shaking it will not come out, and it will give the proper confinement, right? So here you can see this will be discussed again tomorrow, so I'm not going to discuss it in much in detail. The failure of the member subjected to bending and axial load means I'm talking about the column. Now column, because of the gravity loads, because of dead load and live load, which are acting in the vertical direction, and because of the lateral load, this column is subjected to shear force and bending moment. So this column is subjected to axial force plus shear force and bending. So here you can see we have observed that the failure is observed at the ground story, at the bottom of the column or the top of the column, right? Here you can see the failure is observed at the top of the column, top or bottom, right? Here again you can see bottom of the column, right? Here top of the column, right? Now what is the reason? Reason we have to identify. And what is the reason? The reason is this. This is the reason. You have a maximum moment at the top or at the bottom. In the middle portion, the moment is less as compared to the top of the column, bottom of the column, right? And therefore, such kind of failures had been observed either at the top or bottom because there is a maximum moment, right? And therefore, two types of failures will be available is possible here, and that is when the lateral load will act. There is a possible shear failure which is taking place at a diagonal, so it will be like X cracking, right? Diagonal cracking. Here you have a cracking like this, right? So this is the shear failure, and this is the flexural failure. The flexural failure, when the shaking taken place in this direction, this part comes under tension, so failure will start here. When it will move in this direction, then tension will come on this side. So basically during the shaking you will see such of things. at top and bottom of the column where the maximum movement appears, right? So correspondingly, we are providing a closed stirrup at the top, closed stirrup at the bottom, right? And lapping is provided in the middle third. Lapping is for a middle third. So again, I'm not going to discuss this part. This is a 135-degree band. So tomorrow it will be discussed, right? Here you can see this portion. But now we are coming to the our practice, right? So generally we are not doing a good supervision, right? And we are going for the diffusion construction practice. For example, you see when structural engineer will visit the site. Can you tell me when structural engineer will visit the site? Most of the time. Can you tell me? When the structural engineer will visit the site? During column construction, during the slab construction? When the structural engineer will visit? Can you tell me? During casting is fine, but most of the time the structural engineer will visit when the slab construction is going on, because at that moment a larger concrete work is taken place, right? This is a routine practice, I tell you, right? And generally at the time of column construction, the visit of the structural engineer is not that frequent. So the thing is that the most important element as far as the lateral load is concerned, it is column. And during the column construction, generally visit is not taken place, because a lot of concrete work will be taken place during the slab construction, right? So we have to visit. You see, the slab, in my opinion, the slab is the least important element, right? Why I'm saying least important element? The least important element because this is the element which is located at one particular place and which is very heavy. And from earthquake point of view, we are knowing a heavy mass is concentrated at one level. So it is mass into acceleration. So very heavy earthquake force is generated at the slab level, right? And the slab is very strong in its own plane. Slab is very strong in its own plane, right? So the slab is not going to collapse during earthquake, I tell you. Slab is never collapsed during earthquake, right? Slab is the only element who is enjoying earthquake, but it is creating pressure on other elements, right? So the slab is vibrating as a rigid body. When it is vibrating as a rigid diaphragm, then it creates a pressure on the columns, right? And this column is the most important element, and generally this is the most important element we are not visiting. So the practice should be, when the column construction starts, at that moment you have to actually visit, and we have to instruct for the better detailing, whether it's implemented on site or not. You have to observe, right? Then comes the beam column joint. Now, sometimes we are using the different grade of the concrete, right? We are using M25 for the column and M20 for the slab, right? Now what happens when we go for the beam column joint? You see, we cast a column in M25, and then when slab comes, we casting in M20. So as far as the beam column joint is concerned, it is generally cast in M20, right? If we cast in M20, then there is no use of M25 concrete in the column, because you are creating a weakness at the beam column joint by providing. So you have to avoid a different grade of concrete. So you have to provide a uniform grade all the. Then you see, what is our practice for the water cement ratio, right? We are not controlling water cement ratio at site. Generally the engineer, suppose the slab construction is going on, the engineer is worried about the slab construction. So he is always observing the slab, but he is not looking at the concrete mixture where the concrete is. So what is happening, like a contractor is there, and contractor is finding that there is there is a workability is very less, then he will give the sign that pour more water, and the operator will put one more bucket, right, of water. Now we know that if the water cement ratio will increase, the strength degradation is taken place, but we are not observing that part. But when the next concrete batch will come, and we said, okay, now good workability is available, but that workability we are compromised with the increased water cement ratio. So this should not happen. Water cement ratio must be controlled, right? It is as per the design, and that you would observe. And this is one of the most important point in my opinion. If you are able to control the water cement ratio, then you have a better construction. Inadequate compaction, right? Now, what is our practice when we go for the column construction? We are preparing the formwork up to the bottom of the beam, and then we are pouring the concrete from that height, right? When you are pouring the concrete from that height, then you see the problem is with the compaction, right? So if it is a 10 feet height, and if the depth of the beam is maybe we assume a 2 feet, so 8 feet, that is a column height, and we complete the formwork of 8 feet, and then we are pouring concrete at from the height of 8 feet, which is not proper, right? So that is the one problem, that we are pouring the concrete at 8 feet height, and then at the same time you are not able to do the compaction. So what you do, you take the hammer and then you are tapping the formwork, and by this way you are compacting concrete, which is the improper thing, right? So inadequate compression is another case. Then we are knowing that the top and bottom of the column is going to observe the highest bending moment, right? But when constructing the column, we are constructing those 200 mm separately, because we are constructing column up to beam bottom. Up to beam bottom we construct the column, and then the rest of the column is constructed with the slab. So this is cast separately. That is the problem, right? And which is the most critical section. So, and the poor quality control, right? Now here the poor quality control means I am saying that suppose improper material is supplied on the on the site. The site engineer has to reject that material, but he is so kind enough. He said that, okay, why should I make a loss to the for the aggregates or the cement? So he allowed that. Okay, next time you better go for the better quality of the aggregates, right? So you are not able to reject the material, the poor material on site. So that is one of the major problem we are facing. We are so generous. That is the problem. We have to be very strict as the quality is concerned, right? Then we are talking about the non-structural part. We have a parapet or glass facade. For example, how we construct the parapet. We construct the slab and then we construct a masonry wall on it, right? And what is going to happen? This is good as far as the vertical load is concerned, but when the shaking starts in horizontal direction, then because there is no connection between the slab and this masonry, it may be lose contact and it may topple. For example, these are the Gambis which are generally used for the decorative purpose as for the parapet, and because of the shaking, this is not properly fixed, it may fall. Now imagine this is a very beautiful building, and when you come out of this building during earthquake and suddenly something drops on your head and you die. This is very, so such kind of things should not happen, right? This is the non-structural failure. So what is the ideal way? Ideal way means you have to take the slab reinforcement and then you have to construct a parapet by using the RCC, and the slab and the parapet should be connected so that during the lateral force no failure will take place, right? Then the next part is the liquefaction. Now what is liquefaction? Liquefaction means we are talking about a cohesion-less soil. You see, if I'm explaining the liquefaction in a very simple way, I'm saying the soil is getting strength from two aspects. One is cohesion, another is friction. So C and phi. The strength of the soil depends on C and phi, right? Now, if I'm saying my soil is cohesionless, if it is cohesionless, then C is 0. So then the strength of the soil depends on friction, that is phi, right? So in case of a cohesionless soil, suppose if your structure is resting on cohesionless soil, then what is going to happen? Then what is going to happen? Then you see, when during earth, if water table is high, water will come up, and when the water will come up, the space between the particle is filled up with the water, and if it is filled up with the water, then the friction will be eliminated and there will be no friction. So in cohesionless, there is no cohesion, and now because of the rise of the water table or rise of the water, there is no friction. So the soil do not possess cohesion, soil do not possess friction, so it behaves like a liquid. It behaves like a liquid, right? So this phenomena is known as soil liquefaction. It means soil will lose all its shear strength, because of the increased pore pressure, right? And therefore this problem of liquefaction is occurs most of the time in cohesionless soil, right? Very simple example. Suppose if you try to walk on water, then what happens? You are not able to walk on water. Reason is this water do not possess the shear strength, and therefore you are not able to walk. Same way, when your structure is resting on cohesion, and during earthquake, when the water table comes, then this soil behaves like a liquid and it loses all its shear strength, and then your structure is not going to be supported by the soil, and liquefaction will be observed. Now you can see here liquefaction is observed. This is the better picture. You can see nothing has happened to this building, only the tilting is taken place, right? Because of the liquefaction. Now you can see here, this building is absolutely fine. Nothing has happened from top to bottom. Only the tilting, right? Only if you can make it straight, again you can use this building. It is so good. But we cannot do that, and you can see this is the tilting taken place, right? You can see here, this is the tank which is got tilted during the Bhuj earthquake, and again this tank is again made functional after the earthquake by taking the required measures, right? So basically, factors for good seismic performances. The most important part is this architectural configuration, simple and regular configuration. Therefore, I'm always saying that you compare the structures in advanced countries. They have learned a lot from the past earthquakes, so they believe in the simple and regular configuration. Because when you are making your structure irregular, then you are actually inviting torsion in your structure. So you are not able to handle earthquake force properly, and in addition to that, you are inviting torsion in your building. So you are making your life miserable, I tell you. So as far as configuration is concerned, it is the responsibility of architecture, and we have to ensure that simple and regular configuration is there, right? I'm giving you a very simple example. Suppose okay, we'll discuss later on. First, we complete this. The second part is the structural design part. The structural design part, we have to ensure these four things. This is very important. Professor Murthy has already mentioned adequate lateral strength, stiffness, ductility, and the integral action. These are the four important parts the structural engineer has to provide, right? So this is very important from this purpose, and then we have to consider the effect of non-structural element also. You see, in RCC structure, we are providing infill walls, right? infill walls. Now these infill walls are not designed to take any load, right? The infill walls means we in RCC structure, the load is transferred from slab to beam to beam column joint to column to foundation. This is the way we are transferring the load. We are placing the infill walls for the functional purpose only. Functional purpose means I want a room, I want an auditorium, so I am placing the walls. It is not designed to take any load. But during earthquake, what is happening? Your whole structure is vibrating, and this infill wall is sandwiched between the two columns. So this infill wall is also going to vibrate with the columns, and therefore it is not designed to take any load, but it is still going to participate in earthquake event. And because of these infill walls, the stiffness of the structure will increase, right? So we have to count the stiffness of the non-structural element also in the design as far as lateral load is concerned. And the last is a quality of construction. This quality of construction is the most important. A better quality, if the quality control is there, is you see if you go to the Dubai and other countries, then third-party inspection is there, and the third-party inspection, then they will come to site at any moment and they take the sample and they test it, and if they find that the quality is not good, then they will issue the notices, right? And the contractor has to improve the quality of construction, right? But in India, we are not going for such things. Third-party inspection, site inspection is not there most of the time, except in certain projects, right? So for the quality to improve the quality of construction, the third-party inspection is important. But in India, suppose if you go for the third-party inspection, again there are more chances of corruption. So we need a good third-party inspection to make a better quality of construction, right? So the very simple conclusion is derived is that for the safety in future earthquakes, simple thing, all provisions of the code should be followed in design and construction. Only you have to follow the codes, that's all. I think this is good enough if you follow the code even, right? So this should be made mandatory. And you have to understand that the retrofitting of an existing inadequate building involves 4 to 5 times the initial cost, initial extra expenditure required on seismic resisting features, right? So retrofitting is quite costly. It is 4 to 5 times costly as compared to the initial expenditure required for the seismic resisting features, right? Fine. So up to this, I think we have discussed a basic part of the behavior of the structures. And tomorrow we have one more session. It is on the laboratory experiment. We have a good laboratory here, and I will show you some of the good videos here, and the failures and everything we'll see. And you see, the thing is, if you observe anything, then you will remember it for a longer time, right? So here, if you perform an experiment in the laboratory and if you see the failure, then definitely you can conclude everything very fast, right? So we'll see those experiments tomorrow in the afternoon session. Now, what are the initiatives taken place in Gujarat? What are the initiatives taken place? The initiatives is the earthquake engineering subject was introduced. You see, this is again, the earthquake subject was introduced in 2003, and 2016 it was become elective. You see, this is happening in education. People are forgetting earthquakes, and same with the university also forgetting earthquake now. And now we are waiting for another big event, and then again the new resolutions will come in picture. After earthquakes, the training of engineering teacher was taken place, training of engineers was taken place, the awareness about the building was there, mason training and certification was started, seismic microzonation of certain area has been done, seismic code revision was taken place, and in Gujarat, the two good institutes comes in picture: Gujarat State Disaster Management Authority and Institute of Seismological Research, right? Now, what the GSTMA is doing? The GSTMA is authority which is try to manage the earthquakes, and the ISR is actually observing the earthquakes in Gujarat. ISR is the Institute of Seismological Research. ISR has placed a broadband seismometer all across Gujarat, and maximum broadband seismometers are placed in the Kutch region, and the whole Gujarat is covered, and they are monitoring from Gandhinagar, right? And they are observing the seismic events. The small earthquakes, even of 3 magnitude, it is recorded on this broadband seismometer. And if you download the application of ISR, then you come to know that each and every day small earthquakes are coming, right? So this is these are the good things which comes in picture. But you see, in my opinion, these organizations are really good, but you need a technical competency, right? You need a good structural engineers, right, for the capacity building. No such institute will come up in Gujarat, right, which is required to make our structure safe. This must not happen. But the Gujarat Professional Civil Engineering Act 2006 came in picture, right? Now, as per this act, the mason certification or licensing of engineers, so some regulation it is framed out in this act in 2006. But you see, in 2020, it is not fully means it is not actually implemented properly, right? The Gujarat Professional Civil Engineering Act is not implemented correctly till today, right? So what are the actions required? The main part is certification of the mason, right? That is to be required. So good masonry work is required, right? So right now the Gujarat Institute of Disaster Management is involved in the mason training in Gujarat, and it is still going on. It's good. The competence-based licensing of the engineers, right? Now, how the licensing has been done, I tell you. Suppose I completed my Bachelor of Engineering, right? I completed my Bachelor of Engineering, and when I completed my Bachelor of Engineering, now options are available that I can do my BE Civil without taking more subject of structural engineering, right? Then I go to the field. Now, as I'm undergraduate, so I'm the authority is not giving me license. But after 5 years, you are eligible for the structural design, right? So you see, it is not based on your knowledge. License is not given on the basis of your knowledge. It is given on the basis of experience, which is something wrong, right? So here, actually, the Gujarat Council of Professional Civil Engineers, if this act will be actually properly implemented, then I think we can have a good result. Then requirement of peer reviewed of important projects. Peer review is required. The structural documentation, right? Now I'm giving you a very simple example. Suppose if you are buying a bungalow. Now the cost of your bungalow is maybe a 2 crore, and you are spending 2 crores for your bungalow. Now when you purchase, what exactly you will get from builder? You will get a document. Which document you will get? You will get the document, means legal paper, that this is the ownership document, right? This bungalow is now yours. That is one. And the architecture plan you will receive, but you will never receive the structural drawings or design, right? Now when you purchase a 2 rupees glucose biscuit, and when you purchase a 2 rupees glucose biscuit, the all content is written on that wrapper of the glucose biscuit. What is there in the one glucose biscuit? This much sugar, this is flour, this is wheat, which is there. But when you are purchasing a bungalow worth 2 crore rupees, you don't know what is there in the beam, what is there in the column, what is the reinforcement in the beam, what is the reinforcement in the column. Nothing. You are not knowing anything, and that is the problem, right? So suppose You see, the people are hesitating. The reason is they are knowing that if the design is not okay, then you will they will be in trouble, and maybe you approach the court and they will be in trouble. So that is the problem. So therefore they are not allowing the structural drawings and designing to the owners, right? They are not giving. So we have to, what Murthy sir mentioned, the sample checking of the drawings and constructions drawings should be there, like income tax returns, right? It is not all the income tax return had been checked, but few of them are scrutinized very well. Likewise, structural design to be verified. We are always saying that when a big earthquake will come, it will give you a window of opportunity. For what? For changes in the construction culture and the capacity building. But this is very short and often wasted. This is what happened in Gujarat also. Now the similar type of construction is coming up, what we have observed in 2001 as far as failures are concerned, right? So we have to say that mega earthquake disaster awaits India, particularly in the north or northeast part, Indo-Gangetic plains. And we are knowing that most of the earthquakes, most of the constructions are deficient, and therefore we have to be very careful, and we have to say that we have to believe that solution lies in the building, not in the earthquake. So good practice to be required. So actually the building industry has to respond to this, right? We said that earthquake safety is a long and hard struggle, right? No instant result is going to come. And this morning I had given the example that California started the earthquake safety program 70 years back, and and still it is going on. It started in 1971, right? So if India will start today, then at least we require 100 years to catch up that part, right? And this is very important. This seismic design is a shared architecture and engineering responsibility, right? Seismic design, particularly we are saying seismic design. In resistance to gravity loads, if architect and structural engineers are working separately, independently, there is no problem. But for earthquake, separating engineers from architect is a formula of disaster. This is told by Souza, is a seismic engineer. So architect and engineer has to work together for the earthquake safety. For the gravity loads, if architect and structural decisions are made independently, it's fine. But for the earthquake, it must be discussed, and then decision must be taken. And who is responsible for this? The owner, building owner, has to make architect and engineers to work together, right? So a good interaction is required between architect and engineer. And what is the situation right now in India? In India, architect and engineers are working separately, and because of this teamwork, we are going to have such a result, right? So this should not happen. I think in future we have to take care. Engineers and architects has worked together for the earthquake safety. And basic principle for the seismic design of the building: the cost of earthquake resistance depends on planning and applied approach. No significant increase in the cost. Morning, Murthy sir said when we are spending 1,000 rupees or 4%, means it's only 4 rupees you are spending for the earthquake. So it is quite nominal. We are spending a lot of on the flooring, a lot of on the kitchen and the toilets and bathrooms, right? So we are spending a lot of money in which is wrong. So you have to spend some money for the safety of the structure also. So how much we have learned? I think this will tell you everything, and I think this is a well-known table. You can see long-term human response to earthquake. When earthquake comes, 0 to 1 minute, a major earthquake comes, then actually the reactions are positive or negative, right? But the first minute of the earthquake, no positive result you have, reaction you have, panic is there, right? Panic. You are panicked because of big earthquake. It's 1 minute to 1 week, aftershock continues. So negative reaction means you have a fear that, okay, what happened to my building? This earthquake, aftershock continues. But at the same time, rescue and survival starts. It is a positive reaction. 1 month to 1 week, when aftershock reduces, then short-term repair starts. It's a good sign. But at the same time, now the people will start blaming the builders and the designers and officials, right? It's a negative sign. 1 month to 1 year, long-term repairs will continue. Then 1 year to 10 year, no positive sign, but the interest, negative sign is your interest in the earthquake resistant design will go. And 10 years to next earthquake. Now, what happened in Gujarat right now? It is this thing: reluctance to meet the cost of seismic provisions, increasing non-compliance with the regulations. And then again, a big earthquake will come, and now everything will be repeated again, right? So this is the human response to earthquake, and I think I witnessed this cycle, right? I have not seen the next earthquake. If next earthquake will come, again the major changes will be there, right? But I think we have lost the opportunity to improve capacity building in the area of earthquake engineering. We have done a lot of work in Gujarat, but at the same time, we have not 100% utilized this opportunity. Very good work has been done in Gujarat, I tell you, right? And this is what the picture of Ghazni is, a memory loss, right? And generally we are observing there's a memory loss all the time as far as earthquake is concerned, right? So don't be a Ghazni, and we have to remember this earthquake for the safety of the people, for the better nation, right? And therefore, the Henry Dagenkorb, the structural engineer of California, has said that this is the most appropriate line. So some of us used to argue that you shouldn't really get your structural license until and unless you have chased an earthquake. No matter how much you read the reports, the impact doesn't really strike you until you have seen the damage and casualty, right? This is very important. When you have not seen any damages and casualty, then you don't actually realize the severity of the earthquake. If you have seen at least one earthquake, then definitely you become a good practice. I tell you what happened in 2001 earthquake. In 2001 earthquake, numbers of buildings collapsed. It was 26 January. So 8:46 the earthquake struck the Gujarat, and then actually I was working as an NCC officer, so we have to go for the flag hoisting ceremony. So I reached to the college, and actually we have done the flag hoisting, and other program was cancelled. We did the flag hoisting, and immediately after that, we find that numbers of buildings collapsed in Ahmedabad. So one of the building near LD College, it was collapsed, and at that moment, our NCC cadet go to that building, and it was basically soft story failure, and many people have trapped in that building, and the NCC, our hostel students and the NCC cadets have actually helped them to come out of this building, right? And after that, actually our NCC unit was associated with the army, because army has taken a charge of the collapsed site, and they are actually bringing dead bodies out of the collapse site, and they are also bringing the valuables from the site. So the Indian Armed Forces are the most reliable for that, and our NCC cadets were helping. And I tell you, our NCC cadet brought almost 10 dead bodies, from this collapse site, and I was also there on the site, and I brought a dead body of 4-year-old boy, right? I never forget this in my life, I tell you. When I brought, because I'm civil engineer, but I was working as an NCC officer, so I find myself in a helpless situation, I tell you. And At that moment, I realized that who is responsible for this disaster, right? Whole thing is distracting us, right? As a civil engineer, and I wasn't able to sleep for a month, I tell you. And our cadets have worked a lot, almost for 3 to 4 months, and they worked with the Indian Army. And so the once we have seen this picture, we will never today, if I remember that incident, still the same picture comes in my mind, right? So therefore, you see, we have put a very honest effort, and we try to work very sincerely in the field of earthquake engineering. So therefore, this statement of Henry Degenkolb, that some of us used to argue that you shouldn't really get your structural license unless and until you have chased an earthquake. If you have seen this casualty during earthquake, then definitely you will do the honest practice for your lifetime, I tell you. So this is a statement made by the Henry Degenkolb. So only thing is, pay a little now or a lot later, right? So time is already started. It started, and I think we have not started working on it. Time is already started. So we have to begin with the end in the mind. We have to say that we want an earthquake-safe society. That should be the end in mind, and so we have to begin with this end in mind. And this journey to the earthquake-safe society uh, is uh, is a very long, and we have to climb many ladders. Here we can see that we have to climb this ladder. We are right now at the bottom of the ladder as far as earthquake safety is concerned, right? So I hope we should start climbing this ladder of earthquake safety as early as possible, right? So there's the last message I want to give. This let us prepare ourselves to reduce earthquake to a nuisance rather than danger. Convert earthquake disaster into a routine event. Right? That is to be required. Right? So reduce earthquake to a nuisance rather than danger. Right? Convert earthquake disaster to a routine event. What Japanese people have done. This is the thing we have to do here. Right. So if you have any question, you can ask, and wish you all the best. And thank you very much for your patient hearing. My special thanks to Professor Murthy and Professor Jain, who are my gurus, and I learned most of the things from them. Right. So if you want to ask any questions, you can ask, please.
Thank you, sir. Thank you very much.
If you have any question, you can ask. Already I exceeded my time, but 15 minutes it was there in the first lecture. So I took 15 minutes in this lecture more, right? So
Good afternoon, sir.
yes,
Sir,
good
is this
afternoon.
audible
Please.
to you?
Yes, please.
Sir, that was a very informative presentation, and your effort during the aftermath of the Bhuj earthquake is very appreciable. And sir, I have this question regarding the short column effect.
Yes.
Sir, in the previous session, you told us that the earthquake identifies the weakness, and stiffness means I know that stiffness means resistance to deformation. So
Yes.
why does it happen that uh, uh, the short column only attracts the higher earthquake force when it is more stiffer than the long column?
You
I
see,
mean, being stiffer, it should attract the lesser force.
yes. Good question. Suppose if you take, okay, I'll explain with a PPT. Okay, 1 minute. Suppose if I'm taking right. Now you have a column here, you have a column here, you have a column here, right? You have how many columns? 9 columns you have, right? Now, if this column becomes short, now what is going to happen? You see, remaining columns, but suppose if all columns are not able to, means not a single column is a short, right? Suppose not a single column is short, and the deformation delta of each column is suppose uh, a delta is suppose 10 centimeter, right? The deformation of every column is 10 centimeter, right? Now what is happening? Suppose a middle column, this middle column become short. If middle column will become short, then what is going to happen? Now the middle column becomes short. So suppose if I'm saying okay, okay, I'll take one by one. Suppose a 900 kilonewton force is there, right? 900 kilonewton, right? All columns are same. So all columns will, how much load? How much load will be taken by each column? 100? Yes or no?
Yes, sir. 100.
100 will be taken, right? Now again, what I'll do? I'm saying that okay, this is the same thing, and here there are 9 columns again, but out of these 9 columns, 8 columns are okay, but the one column, this column is a short column. This is a short column, right? Now what is going to happen? What is the stiffness? What is the total stiffness? Now if I assume the length is L by 2, for example, right? Then the stiffness of this is K. Stiffness of this is K. Stiffness of this is K, right? And what is the stiffness of the middle column?
8 times K.
It is 8 times K, right? So what is the total stiffness? It is basically 16K, right? Total stiffness will be 16K and divided by 900, right? 16K 900. So actually, how much load will be taken by the middle column? If you divide by
Yes, sir. 8 times K.
just calculate the 900 divided by 16 multiply by 8. So the middle column will take 450 kilonewton now. Middle column will start taking 450 kilonewton load, and the remaining will be distributed among other 8 columns, and other 8 columns will take only 56 kilonewton. You get my point? This column will take 56 point something, but this short column will take almost 450 kilonewton. वो 450 kilonewton लोड लेगा. अभी उसकी कैपेसिटी क्या है? What is the capacity?
100 kilonewton.
100 की वो 450 लेने का प्रयत्न करेगा तो क्या होगा उसका? उसकी हालत खराब ही होने वाली है. You get my point? And therefore the short column is not good. Short column, you see, it is without our knowledge, it start taking more load, right? If we know that this column becomes short, then we can design. But if you don't know that the column became short, then there is no solution for this, right? Is it clear?
Yes, sir. Thank you, sir.
Yeah. So if you have any more question, please. I love to take questions, right?
Sir, is this is the short column effect also applicable on the basement floors? which are constructed underground.
Anything which is above foundation, the short column effect will comes in picture. Anything
Okay.
above foundation, right? Yeah.
Thank you, sir.
Yes. Any more questions? Yes, Vivekanand. Vivekanand Shetty, please. Can anybody unmute? Yeah, please. Please, sir.
No, sir.
Any more question? Vivekanand Shetty. Okay, no.
No,
Mehul?
sir. No, sir.
Okay, thank you. Mehul?
Sir, I have one question, sir, regarding
Yeah.
soft story.
Yes, yes, please.
Sir, in soft story, we are considering 2.5 times of the load, 2.5 times for
Yes,
load.
yes.
But
Yeah.
this is without factor of safety or this including factor of safety. That is,
You see, your question is good. You see, as far as codes are concerned, codes are giving factor of safety 1.2, 1.5. It is given in the code, right? But you have to understand this factor of safety given in the code. It is on a reduced load. On a reduced load.
Okay.
For example,
Right, sir.
actual load on your column is 100. You see,
2.5. Suppose the load is P, design load is P, will design for 2.5.
Yes,
Then
yes.
the ultimate load will be 2.5 multiplied by 1.5. Right, sir?
Yeah,
Am I right?
yes. So,
Thank you, sir.
yeah, actually, what happens? I tell you. Uh, you see, actual load on the column or the structure is coming 100 kilonewton. You are designing for 20 kilonewton, 30 kilonewton, right? And you heavily rely on ductility. So when you design for 20 kilonewton, 30 kilonewton load, and then you apply 1.5 factor. So 30 into 1.5, it becomes 45,
Yes.
right? So it is well below the actual load coming on the column. So it is always dangerous, and therefore I am saying earthquake resistant design is a challenge. Earthquake resistant design is a challenge because actual load coming on the column is 100. You are designing for 45, and still you are saying my structure is safe. The reason is you are ensuring that the amount of energy absorbed by your is okay. It is actually the earthquake supplies the energy, and your structure is absorbing that energy, and therefore
Yes, sir.
yeah.
Sir, even you are proposing the shear wall on in soft story. Even in spite of that, we have to consider 2.5 times.
No. You see, sometimes what happen? No.
Shear walls.
No. Sometimes what happen? Like people are saying, "No, I don't want to put shear wall. I don't want to go for the bracing system." Then in that case, you have to design for 2.5 times force, right?
Okay, right, sir.
Yeah.
Sir, one more, sir. In that case, displacement for pounding that 0.04 H, and again you have that step for 0.04 HR. You said that. What is this R?
Sir, this R is a response reduction factor.
Response. This is mentioned in IS.
Yes, it is mentioned in the IS code. Basically, this response reduction factor depends on three things. It's a ductility, overstrength, and redundancy. So
not on foundation relationship.
Majority depends on ductility. So ductility means if your structure is ductile, it is going to deform more, right? If I'm saying my moment resisting frame is ductile, means it is going to deform more. So its R factor is 5. If it is an ordinary moment resisting frame, your R factor is 3. Right.
So generally, R is greater than unit or less than unit.
It is more than one. More than one. Yeah.
Thank you, sir. So nice. Thank you, sir.
Yeah.
It's a great, sir.
Yeah. Thank you, sir. Anyone else? Yes. Manish Kumar.
Hello.
Behul. Okay. Yeah.
Okay. So my question is, if more mass and more stiffnesses are attracting more inertia forces, right? Then, if more mass and more stiffnesses are attracting more inertia forces,
yeah.
Then if
we will talk separately about this mass and stiffness, right?
Yes. Okay.
If mass is more, earthquake force is mass into acceleration. So earthquake force will increase. This is the first thing, right?
Right.
Second thing, talk about the stiffness, right? Now stiffness, when a stiffer member is there, it is always good in your system, because the stiffer member will reduce the deformation. It is good. But in the short column, what is happening in short column? We are not knowing it becomes short and we start taking more load. That is the problem, and therefore short column is not good. But if a stiffer member is there in your system, it is always good because it controls the deformation of the structure, right? So yeah, stiffness, higher stiffness is generally good. It allows a less deformation, right?
Okay, right. Because stiffness is resistance to deformation, right?
Yes, yes.
If we are supposed to damp the forces, right?
Yeah.
Which any kind of stiffness, or say tune mass damping, maintaining the center of stiffness and center of mass, where it should be connected to interior columns or directly, or say outer peripheral columns with some kind of system like outriggers.
You see, generally center of mass and center of stiffness, it is always within the building. It is good, right? It should be within the building, right? And eccentricity should be the minimum. It should be the minimum, right? And you have to ensure that to avoid the torsion, the symmetry should be there. Right. What you are saying, outriggers is altogether different aspect, but center of mass and center of stiffness is always within the building, and you have to ensure they both must match, and then you avoid the torsion in the system.
Okay.
Yes, Manish Kumar.
Yes, sir.
Please.
So I have this one question.
Yes.
Sir, why are the shear walls provided on alternate base? I mean, why not continuously we provide shear walls?
Alternate base means, that is the reason. You see, basically the purpose of shear wall is to increase the stiffness,
Yes,
right? And the purpose is also we have to utilize the space which is available at that particular story. So we allow the vehicle to park there. So we have to give the passage for the vehicles to park. Otherwise, the space will be unutilized. That is the reason. So for the parking, we are providing a shear wall at certain distance, and almost 20%, 30% shear wall, which will eliminate the difference in the stiffness. Because when you put the shear wall, it is in 2 meter, 3 meter long. Then as far as stiffness is concerned, stiffness is very high. So it will eliminate the difference of the stiffness, right? Yeah.
Thank you, sir.
Yes. Anything else, please?
Good afternoon, sir.
Good afternoon, please.
Hello.
Yes, please.
Sir, my question is that how we can manage relation between stiffness, flexibility, and or we can say magnitude of earthquake. Hello.
Stiffness and the intensity. You see, again,
stiffness, flexibility, and intensity.
Stiffness and flexibility are inverse of each other.
Yeah.
Right. Stiffness is load required for unit deformation, and the flexibility is deformation due to unit load. Right.
Yes, sir.
But what the intensity you are saying? Intensity. Right. This is you are talking intensity of shaking.
Yeah. Yes, sir. Yes, sir.
You see, I already explained that. Suppose a simple question I'm asking you. Which type of building will be affected more, high rise or low rise during earthquake? Tell me.
If there is amplitude of earthquake is high, then high rise building will affect mostly we can say. Hello.
No, that is not the correct answer. Anyone else? Basically, what happens? I tell you. You see, it depends on which frequency earthquake contains. Right. Suppose earthquake means earthquake is of a low frequency. low frequency, then our structure which having a low frequency, then what is happening, the frequency of the structure and the frequency of shaking matches, and this is known as a resonance, right?
Yes, sir.
It
Yes,
means
sir.
high-rise building is having a low frequency, and if earthquake is of low frequency, then it will affect the high-rise building.
Yes, sir.
And if earthquake is of high frequency, then a structure whose frequency is high will be affected. So low-rise building is having high frequency, so low-rise will be affected, right?
Yes, sir. Yes, sir.
Yeah. Tomorrow we will see this resonance criteria, right?
Yes, sir.
Tomorrow
Yes.
we will see. Yeah.
Then sir, what is the effect of stiffness and flexibility will affect? How we can manage the flexibility and stiffness of the structure?
You see, when you go for when you try to make your structure flexible, it means you are allowing larger deformation. That is one thing.
Yes.
So
Yes, sir.
you have to ensure that how much deformation you want to allow in your structure. This is the first part. And
Yes, sir.
as far as concrete is concerned, concrete is having limited deformability, and therefore, if your structure is very flexible, then it will result into a bad performance. So therefore,
Yes,
your
sir.
structure should be stiff enough so that a deformation is controlled, and you will not going to observe a greater damage, right?
Yes, yes, sir.
Yeah,
Okay, thank you, sir.
yeah. Welcome. Anyone else? Manish Kumar, you have raised your hand. Any question? Vivekanand ji, you have raised the question. You have raised your hand.
No, sir. Hello, sir.
No. Yeah. Okay. If you don't have more questions, then I think we can stop here for the day.
Hello, sir.
Yes, please.
Sir, Mr. Anuj Kaushik Kumar has raised a question in the chat box that whether we can use bamboos as an alternative of reinforcement in columns or not.
You see, you can use bamboo as a option, but the life of the bamboo is again a question, right? And it depends for which purpose you are using bamboo, right? Definitely, bamboo is good enough for the traditional housing systems, right? And we have some of the classes on the last day on the traditional housing system. I think you will come across the bamboo construction at that time, right? But like in RCC, if you use the bamboo, then the purpose will not be served because the life of the bamboo is not that great. That is the reason, right? But for the traditional housing system or for the rural housing, you may use this bamboo, right?
Yes, sir.
Yeah. The Subhash has mentioned the Indian dynamic codes not revised in recent 20s. Whether updated. You see, not we are not, I'm not talking dynamic codes, but I'm talking about the earthquake codes. Earlier, it was 1984 code revised in 2002, and then it was revised in 2016. So now you see revision is not taken place every 5 years. The reason is, like Professor Murthy is one of the resource person who is putting a lot of effort, but actually as a teacher we have to support them, and our input is required. We can also give our input, and then this frequent revision of the code may taken place, because you see they are very heavily loaded. Few people are working on it, but contribution is not coming from our side. That is the problem. So I think revision of the code should be consistent at a shorter duration, and also uh, taken place regularly, right? Yeah. Anything else?
So, sir, I would like to thank you for delivering such intellectual sessions today. Sir, today we got to learn a lot new things about earthquake engineering, about how earthquake engineering becomes a very crucial subject for the civil engineering branch, and how earthquake resistant practices have been ignored for a long time now in many parts of our country, and how earthquake has disrupted so many lives and properties till ages now. So I hope everyone enjoyed today's day one, and I hope everyone got to learn a lot new things.